This week we visit a nuclear reactor. See how a microphone works. And look at multiple outlet strips. I don't need an outlet. I have batteries. Somewhere.
Hello? Hello? Is this thing on? Must be a live one of these here somewhere. Considering the trouble that Alex Bell and Tom Edison had to come up with the first one, they sure have multiplied. Microphones come in all shapes and sizes because there are several ways to do what they have to do. Now, I was tempted to use this to introduce what a microphone did, but it doesn't. Two cardboard cups connected with a string will transmit sound from place to place, but only if the string is tight. Can you imagine trying to build a telephone system out of this? How would you connect the various phones together at the right time? The microphone changes sound wiggles in the air to wiggling electric current, and that can be carried by wires and switched and connected conveniently. The electrical wiggles can also be recorded conveniently. This is Tom Edison's carbon microphone. It launched the telephone system and modern broadcasting. Inside is a bundle of loose carbon grains. A diaphragm like your eardrum is connected to the carbon grains so that it compresses and decompresses the grains according to the sound waves falling on it. The amount of electrical current that the grains will pass is proportional to the amount that they're squeezed. The wiggling electric currents that this produces are an analog of the sound pressure wiggles that hit the diaphragm. Hello? Hello? The carbon microphone has a couple of drawbacks. The sound waves are forced to do a considerable amount of work, squeezing those grains. This has some mechanical implications that affect its sound. And since it operates by wobbling an external current, it requires a source of external current. Early carbon microphones also required a periodic whack to loosen the grains. This ushered a century of people tapping microphones before they spoke into them, and the tradition continues. This is better. It's a dynamic microphone. It still uses a diaphragm, but it creates tiny electrical fluctuations using a moving coil of wire glued onto the diaphragm. The coil of wire moves in a magnetic field, and the electrical wiggles are produced the same way as an electrical generator. Since the sound pressure fluctuations are creating current by the no free lunch theory, they're still doing some work, but it's a lot less work than in a carbon microphone. Since the currents are so tiny, electronic amplification is always needed with a dynamic microphone. Because it doesn't have to do much work, though, the diaphragm can follow the pressure fluctuations more faithfully. The dynamic microphone is the same as a loudspeaker in reverse. Putting Acme's money where its mouth is, or more correctly, putting Acme's mouth where its ear should be, we offer the following proof of that last statement.
Hello, hello. Of course, anyone who's used a two-way intercom already knew this.
This is even betterer. The electric condenser microphone has just about wiped out all other mics. It's now in cassette recorders and most telephones. The condenser part of the name comes from a long time ago when experimenters thought that collecting electricity was a matter of condensing it. We now call condensers capacitors. You can make a capacitor by holding up two sheets of aluminum foil like this. If you apply an electric potential to the sheets, electrons will run from the more negative one to the more positive one in an attempt to balance the universe. When you take that potential away, the electrons will create an electric current by rushing back to where they were. The capacity effect is proportional to the surface area and inversely proportional to the size of the gap. Early condenser microphones used a 400-volt power supply to polarize the plates. The supply was the size of a loaf of bread, and the sheets were, well, a little smaller than this, but not much. Sound pressure fluctuations wobble the gap, and the wobbling electric currents can be detected. The only work that the sound waves do is to move the diaphragm. The electrons and the power supply do the rest. The electric condenser uses a permanently polarized capacitor. There's no power supply. But by a kind of a curious irony, the signal's so weak that it can't even make it through 6 feet of wire. So all electric condenser mics have an amplifier right inside the microphone capsule. The amplifier does require a power supply, but a simple 1.5-volt cell is enough. When the unit's in a telephone or a cassette recorder, the power supply is the same as the one from the device. Electret condenser microphones work incredibly well, and they cost about $1 retail. An aunt of mine once complained that she was annoyed by scenes in movies where the actors were seen in great big spaces, talking. She got distracted, wondering where the heck the microphone could possibly be. Actors often have this, a radio mic. This tiny capsule is the microphone. The bulky box is the transmitter. This radio mic costs thousands of dollars because it has to work perfectly. It doesn't, but that's another story. See, great performances shouldn't be interrupted by a tiny piece of static or an occasional hiss. If you can stand the occasional imperfection, the $100 variety is available for your camcorder. The microphone capsule has to be located about here to pick up the actor's voice properly. Although under the right circumstances, it can even be concealed in the hair. The right circumstances, of course, include having enough hair to conceal a microphone. So mine's right here. The radio transmitter can go anywhere that it won't be seen. Often it's on an ankle, usually on the belt of the back, or even inside a jacket pocket. If you're sitting through a boring movie, you can always look for radio mics. Look for a wrinkle in the clothing or a lapel line or a piece of sticky tape's holding the microphone on. You can also look for the transmitter bulge, and sometimes you'll find this antenna working its way out of the clothing. So, Auntie, can you hear me?
A cameraman's work is never done. An armatron's work is never finished.
Nobody seems to like nuclear power plants. This fact alone qualifies the subject as an excellent Acme item. But beyond that, these Canadian can-do nuclear power plants do have some likable qualities. For one thing, they're kind of simple. You can build a can-do reactor in your basement if you like. All you need are some of these fuel pellets and some heavy water. The pellets are natural uranium as it comes from the ground, refined and turned into a ceramic. The pellets go into bundles like this. The bundle of fuel needs to be surrounded by heavy water, deuterium. Deuterium is present in ordinary lake water. It just needs to be separated. Normally in nature, uranium is always decaying into a lighter element by emitting some of its neutrons. Normally these neutrons whiz away so quickly that they have little significance. As a matter of fact, the can-do uranium pellet can be held safely in your hand. Things change when you immerse the pellets in heavy water. The deuterium slows down the whizzing neutrons to the point where they have a good chance of colliding with another uranium nucleus. This will cause the release of another neutron or two, and so on. This is the famous chain reaction. The reaction produces various radioactive products and heat. Because the heavy water slows down the travel of those whizzing neutrons, it's referred to as a moderator. To complete your homemade nuclear reactor, you need a boiler and a steam-powered electric generator. To keep with can-do design, the plumbing gets connected like this. Circulate heavy water around your fuel pellet bundle. It will heat up. In a separate plumbing circuit, circulate a different batch of heavy water to take away all the heat that's generated by the reaction. This heavy water meets ordinary water in a heat exchanger. The two waters don't mix in the heat exchanger, but the heat causes the ordinary water to boil. The steam from the heat exchanger, or steam generator in can-do terminology, will turn the fan blades of your turbine, and then the turbine turns your electrical generator. You'll need to cool the steam to condense it and send it back to the steam generator. Lake water's handy for this, so a location by the lake is a good idea. By the time you're done building all of this, it will probably fill your entire basement. It'll be worth it though. That little fuel bundle, the size of a rye bread, will run your house for about 100 years. Before you rush out to build a reactor for yourself, you should also know that the can-do specifications call for safety systems that will increase the size of your little reactor by a factor of about 10. you'll need a bigger basement. The Darlington No. 1 reactor that we visited uses 480 of these tubes, each with 13 fuel bundles. The tubes are a tube within a tube to keep the moderator water separate from the heat transfer water. Nuclear power plants are similar to any power generating facility, but a lot cleaner. Every dust speck has to be accounted for. So does every mop, rag, and broom. As you cross various barriers from area to area, a radiation check is mandatory, with particular emphasis on your hands and feet. Having undergone any of several medical procedures at your doctor's office is enough to set off one of these alarms. The reactor itself is hidden behind 2 meters of concrete. After you pass that little barrier, there's an elaborate airlock system. This is the face of the reactor itself. The round things are the fuel bundle tubes. I'm not in any danger here because the reactor hasn't been operated yet, and there's no radioactivity. After the reactor is operated, people won't be in this room, except in protective suits and for a very short time. Each fuel bundle will remain in the reactor for about 15 months. The reactor is refueled while it's still operating by a robotic fueling machine. At the top of the tubes, you can see the plumbing that carries the heat transfer water to and from the tubes. This is the side of the reactor, and these are the poison injectors. Poison, in nuclear reactor terminology, refers to any substance that will absorb those whizzing neutrons and stop the reaction. This is one of 2 safety shutdown systems on the CANDU. This is the other safety shutdown system. These are the tops of the reactor's control rods. The rods are made of a substance that absorbs neutrons. They can be raised and lowered to control the reaction. Normally, the rods are used to balance the heat in various parts of the reactor, but they're held in place by electromagnets. If the power to the electromagnets is interrupted, the rods fall completely in, automatically stopping the reactor. This is the vacuum containment building outside the reactor building. It's always under vacuum. Should a pipe carrying radioactive hot heavy water break, the steam will be whooshed into here. This is not a full solution, but it will allow time for a Plan B to be implemented while the danger is contained. There are too many safety devices and strategies to go into. Basically, the plant is designed to withstand the direct crash hit of a jet airliner, if that makes you feel more comfortable. If you have a hot water furnace in your house, there's a good chance you have one of these. Well, same idea, different scale. This is the motor for the reactor's main circulating pump. It's being installed. It's a 13,000 horsepower job. This is the, it's a pool. One of 2 that serves 4 reactors. It's true that nuclear power has a famous downside. There's no acceptable plan for disposing of the highly radioactive used fuel. Well, there is a plan. For now, used fuel is stored under ordinary water. This is an adequate solution for about 20 years. What the nuclear industry needs is a plan that will allow us to put the used fuel somewhere where we don't need to keep an eye on it. There will be a big prize for whoever comes up with this plan. Until then, well, like we said, it's a pool. This is the turbine hall. Each of the 4 reactors on this site has its own electrical generator. This is a generator. Each one is capable of generating 935 megawatts of electrical power. By Acme's calculations, that's enough to make 1,500,000 slices of toast simultaneously. The generators are big, but they're dwarfed by their steam turbines. A turbine is just a windmill that's operated by steam. Steam that's leaving the first turbine still has some energy left, so it's fed to another turbine that twists on the same shaft. The second turbine has larger blades to recover energy from the expanding steam. Altogether, each generator has 4 turbines on its shaft. The control room of a nuclear power station is probably the only industrial site where you're asked to remove your hard hat. They don't want people saying, "Oh, gee, look at that," and dropping their hard hat on the controls. You might think that a boo-boo in here would cause some sort of a disaster, but the opposite is more likely. The nuclear reaction takes careful monitoring to sustain. Couple that with the safety systems that will shut the reactor down at the least whiff of any variance, and, well, no hard hats, please. This reactor is still under construction, so there are a lot of extra people here. A normal shift will have 2 operators and 2 assistants. There's 2 of everything else as well. Some of the people on this project have been with it for 15 years, even though the reactor hasn't even been fired up yet. By the time Darlington No. 1 produces power, its operators and workers will be familiar with every nut, bolt, pipe, and meter. They'll know the reactor better than most people know their own families. No matter how you personally feel about big power corporations or nuclear power in general, it's reassuring to know that the hardware is in good hands. Your mummy probably told you that this is a bad thing. Public service announcements from the fire department periodically point out that this will burn your house down, and, well, it's ugly. On the other hand, we all have one of these behind our computers. So what makes this okay and this not? History and betterness. In the days before outlet strips, these were in vogue. In the vogue days of the triple tap, there were fewer outlets in the average house, fewer things to plug into them, and the average house wiring was not necessarily up to par. Other than lamps, most of the pluggable household things were heavy current consumers. Things like heaters, toasters, vacuum cleaners, and coffee pots. If the house wiring was properly installed, any 2 of these appliances together could blow the fuse that protected the circuit. If the house was not properly wired, any 3 could likely burn the house down, either by overloading the wiring in the walls or by heating up the triple tap. Today, most houses are properly protected, largely because the improperly wired ones have all burned down now. At the same time, the number of things that we have to plug in has increased in leaps and bounds. The average household circuit is protected from a current flow of larger than 15 amps. The wires in the wall can stand this amount with no appreciable heating. To figure how many things you can plug into one circuit, just keep the total amperage under 15. It's easy for me to say. Our modern electronic wonders are marked in watts. Now, regular Acme viewers are already cringing in fear of seeing this graphic again. Volts times amps equal watts. The wall socket voltage is fixed, or sort of fixed. My father called it 110. I grew up calling it 117, and the electric company will tell you it's 120. Who's counting? Ballpark it at 100. That makes the math simple and allows you to err on the side of safety. So, by the Acme fudge method, a 100-watt bulb draws 1 amp. A 1300-watt toaster draws 13 amps. So, you get 1 toaster and 2 bulbs, or 2 500-watt curling irons and a glue gun. Well, figure it out yourself. Now, before the nasty letters start to pour in, it's definitely not a good idea to run a household circuit continuously at its full capacity. But you'll find that you can run a surprising number of clock radios, computers, and aquarium pumps from one outlet. Our modern wonders use a very small amount of current. And the fact that a 50-watt color television does all of the things that it does and still gives off almost as much light as a 50-watt light bulb should tell you more about the march of 20th century technology than a couple of lousy footprints on the moon. There's a good chance that you'll find the wattage expressed as VA instead. VA stands for voltamps, and it's functionally the same as watts, especially if you use the Acme fudge method. VA's a wimp out for watts and designed to cover up the fact that no one can accurately predict what the voltage in your socket really is. A proper outlet strip has some safety advantages compared to the old triple thingy. First and foremost, the enclosure prevents any malfunction from starting a fire. The thing might burn internally, but it's designed not to start the floor on fire. As well, there's often a local circuit breaker. Don't get the idea that triple taps are no good. As long as you watch the wattage, they're perfect solutions to small electrical distribution problems. Is everybody waiting for me to mention the surge protector? Okay, I mentioned it. The surge protected multiple outlet is a lot like this Acme falling elephant protector. Since I've been wearing it, I haven't been troubled by falling elephants. The surge protector is a component called a metal oxide varistor, MOV for short. It works by being voltage sensitive. As the voltage rises, it lowers its resistance. Under normal conditions, the MOV does very little. If, say, lightning induces an abrupt spike of higher voltage on the line, the MOV shorts it out. Very nice, and the purveyors of paranoia will convince you that this happens all too often, and to not have their product will ensure routine loss of data or immediate destruction, whichever you're prepared to believe. Gee whiz, the MOVs are good things, but they only cost a couple of bucks at the electronics store. In an outlet strip or a multiple outlet thing, they cost up to $50 more. The untold side of the surge story is that most electronic equipment has to be designed to withstand the aforementioned surges anyway. And they do this with built-in MOVs, line filters, and a lot of other safety-related components. In 12 years, operating 14 computers, I've never had a surge. Not so I noticed anyway. I have blown up a lot of computers, but it was always by my own stupidity. If you live in a rural area with long, unprotected power lines, the protector's a cheap insurance. And, you know, like chicken soup. Can't hurt.